Okay, now because of the calculation for a larger n takes more time when using the binomial distribution formula, which is this one here, then of course we have tables that will make the calculation of the binomial distribution much easier and faster and straightforward. So now instead of using the binomial formula, we can use instead the tables that we will discuss, when we solve some problems, of course, that, uses some problems that use the binomial formula as well as the tables. Now these binomial formulas are, present at the end in the appendix B.9 at the end of the book that which is Statistical Techniques in Business and Economics, the text that is used in the this course. Of course, these tables in this appendix, of course, usually are used to calculate the binomial distribution for different sizes of n. As we will see in just a few minutes when we solve some problems using either the binomial formula or the tables. Now, in discussing the binomial formula, it's important that we point your attention to some important notes or points regarding the binomial probability distribution. The first one, of course, it talks about the size of n, whether it is fixed or increases, or the size of y, the probability of success, whether it is constant or it changes. Now, and the first note is that if n is constant, the number of tiles is constant, and y, which is the probability of success, increases from 0.05 to 0.95. Okay, y increases from 0.05, from 5% to 95%. The shape of the distribution changes. The shape of the distribution, it changes. We know that we have different shapes. We have a positively skewed distribution. We have a negatively skewed distribution. Also, we have a normal or symmetric distribution. So the shape of the distribution, it changes once by the probability of success increases from 0.05 to 0.95, and n remains fixed. Of course, when y is 0.05 and n is fixed, then of course we're going to have a negatively skewed distribution. However, when y moves, the distribution becomes symmetrical when, of course, y approaches 0.5. So when y, the probability of success, is equal to about 0.5, then the distribution becomes symmetrical. And if it is, when y is close to 0.05, that is to 5%, then the distribution is, of course, is positively skewed. Now, when y approaches 0.95, of course, then we'll have a negatively skewed distribution. Okay, so when y becomes about 0.95, then the distribution is negatively skewed. Okay, so as we can see, the shape of distribution, it changes from a positively skewed when n is fixed and y is about 0.5, and it becomes normal distributed or symmetrical when n is fixed and y is about 0.5, and then when y increases to about 0.95 and n is fixed, then the distribution becomes negatively skewed. Okay. The second point we will make if pi of probability of success is constant. Now, here, when pi is constant, the probability of success becomes or remains fixed, okay? Say at 0.15 or 0.10, okay? And n becomes larger, okay? Now here, pi is fixed at a certain value, say here at 0.15, and n becomes larger, increases from a certain number to another number, and so on and so forth. Then the shape of the binomial distribution becomes more symmetrical, as you can see in the graph in this chart below here. Look at the chart over here. As you can see here, along the horizontal axis, we have the number of successes, x, and then here along the vertical axis, we have the probabilities. The probabilities here from 0 all the way up to 0.5. Now what happens here? Here we have the pi, the probability of success is fixed at 0.15. However, the number of trials and it changes or increases from n equals 7 all the way to n equals 40. So what happens to the shape of the distribution? As you can see, the shape, moves to becomes almost normal distributed. Here you have is positively skewed, then it fixes itself to become close to normal. Then here is close to symmetrical, and then here becomes very symmetrical. So as n increases and pi is fixed, then we will end up with of course a distribution that is symmetrical. Now we move to perhaps the last topic in this chapter, discrete probability distribution, which is the cumulative binomial probability distribution. Of course, in this topic, what actually we mean when we say cumulative binomial probability, actually it is the sum of probabilities of several outcomes grouped into one event. For instance, probability of x greater than 5 if n suppose is 10. So probability of x, the probability of success of x greater than 5 when n equal 10 suppose, then what we do, we say probability of 6 plus probability of 7 plus probability of 8 plus probability of 9 until we reach the last outcome of the size n, probability of 10. So it is the sum of probabilities. This is what actually we mean when we say cumulative. We just add the probabilities of several, of course, outcomes. For instance, say we want to find the probability of a number of successes x greater than 5, or x less than 5, or x greater than or equal 5, and so on. So probability of x greater than 5 is probability of x equals 6. Of course, 5 is not included because we're talking about x greater than 5. So probability of x equals 6, or x equals 7, or x equals 8, or x equals 9, all the way till x equals 15, because we have here, of course, the number of trials is 15. Okay. Okay. Suppose the number of trials we have is 15. Now, let's say if n equal 15. Okay, so we are finding the probabilities of different, axes, different number of successes, given that the total number of trials is 15. So so probability of x greater than 5 is equal probability of x equals 6 all the way to probability of x equals 15. And since outcomes are mutually exclusive, then we use the special rule of addition, when we find the probability of, the addition probability of, x equals 6 or x equals 7 or x equals 8, then the probability of x greater than 5 is going to be equal to the sum of the probabilities. This is the special rule of addition. when the outcomes are mutually exclusive. So we add them. Probability of x less than 5, we're talking about probability of x equal 4, plus probability of, or probability of x equal, or x equal 3, or x equal 2, or x equal 1, or x equal 0. So here, as you can see, we sum all these probabilities. As you can see, the process of addition is very tedious, and lengthy. So the same thing, probability of x greater than or equal to 5. So here we're talking about, x greater than or equal to 5. So it's equal, probability of x equal 5, plus probability of x equal 6. 5 here is included. Okay? So probability of x equal 5, plus probability of x equal 6, all the way to plus probability of course, x equal 15. Now, instead of, going through this messy calculation of very long additions of probabilities, we use the complement rule. The complement rule, which is we studied in the previous chapter, it makes the calculation much easier. So if, for instance, probability of x greater than 5, since m is what? M is 15. So you get to add probability of x equal 6 plus probability of x equal 7, all the way till x equal 15. So lengthy. So instead of that, you use the complement rule. So probability of x greater than 5 is equal 1 minus probability of x less than or equal to 5. Because here, x greater than 5, when we did over here, we added probability of x equals 6. So the complement, we have to start from x equal 5. Okay? So here it's going to equal 1 minus probability of x less than or equal to 5. Here it is easier than adding all those probabilities all the way to 15. So what you do here, 1 minus probability of x equal 5 plus probability of x equal 6, x equal 5 plus probability of x equal 4 plus x equals 3, 2, and 1, and 0. Easier than calculating all probabilities up to x equal 15. Okay? Same thing, probability of x greater than or equal to 5 is going to equal 1 minus probability of x less than 5. Why less than 5? Of course, probability of x greater than or equal to 5, we're going to start from x equal 5. It's going to equal probability of x equal 5, because here is greater than or equal. So we get to start from x equal 5 plus x equals 6 plus x equals 7 all the way to 15. Now, what's the complement of this? Is going to be equal probability of 1 minus probability of x less than 5. Because 5 is included here, so 5 is not going to be included in the complement. So if we have x greater than or equal to 5 in the left side here, in the right side, we're going to take off the equal sign and becomes 1 minus probability of x less than 5. The same thing here, probability of x less than 10. Okay, here we need probability of x less than 10, which means probability of x less than is equal probability of x less than equal probability of x equal 9 plus probability of x equal 8 plus probability of x equal 7 all the way to 0. So instead of going through all this process of calculation of adding probabilities, now what you do, we use the complement rule here. Probability of x less than 10 is going to equal 1 minus probability of x greater than or equal to 10. It's easier to do the complement than doing the probability of x less than 10. Okay? For instance, here, notice also the following keywords when you encounter these keywords in any problem. Okay? Smaller than is the same as, lower than is the same as less than. So we use this inequality sign to indicate these type of keywords. Okay? So if you see a question or problem, terms like greater than, or more than, or higher than, these mean the same thing, and they mean greater than. This inequality sign, greater than. Same thing if you see any question or any problem, the keyword at least is the same as at minimum, which means at least we started greater than or equal. Probability of x at least 7, that means 7 and more than 7. Okay, so at least we use this inequality to mean at least. To mean this keyword at most, okay, it's maximum. Okay, we use this term less than or equal, at most. Okay, at most 7, from 7, okay, 7 is the highest and going through, to 0. And let me just, use something else here. Okay, let's see, elaborate on this one, for instance, here. Let me erase over here. For instance, probability of x greater than or equal 5. So it's going to equal 1 minus probability of less than 5. Okay? Which is equal, it says like this, 1 minus probability of x equal 4 plus probability of x equal 3 plus probability of x equal 2 plus probability of x equal 1 plus probability of x equals 0. So what you do, you just get the probabilities of all these, and then you subtract that from 1, and you come up with the value of probability of x greater than or equal to 5. Okay, and the others also the same thing here. Okay, for instance, probability of x less than 10, which is equal 1 minus probability x less than greater than or equal 10. Okay, which is equal 1 minus, open a bracket, okay, and we say probability of x equal 10 plus probability x equal 11 plus probability of x equal 12 plus probability of x equal 13 plus probability x equal 14 plus probability of x equal 15. Okay, assuming that we have 15 trials. So as you can see here, we make it simpler and easier and faster to calculate the probabilities, sum of probabilities, okay, if we use the complex. Okay, now we're gonna move to giving examples, to apply the problems or to apply the concepts discussed in this chapter. So we're gonna start with examples. The first example, it is a problem here. It says in a recent survey, 20% of homes in Lebanon were found to have a solar energy. In a sample of 10 homes, what is the probability that all 10 homes have solar energy? B, less than 6 homes, of course, homes have solar energy. Part C, at least 2 homes have solar energy. Part D, at most 3 homes have solar energy. Part E, none of the homes have solar energy. Let's solve the equation. So the first part says, of course, all 10 homes have solar energy. So we're talking about probability of success, which is equal 10. Probability of x equal 10. So probability of x equal 10, we could use the binomial formula, and we're going to come up with 0, 0, the answer. Okay, if we use the table, the binomial table, this is, a kind of, drawing of the table that only shows the probabilities when by equals 0.20. Okay, the binomial tables will look like this one over here, where you have here the probability of success, and you have here the probability of successes. Okay, and then here you will have the bar. Okay, Okay. So here, okay, as you can see, along the column here, you're going to have, successes, whether probability of x equals 0 or 1 or 2, all the way till 10. And over here, you're going to have the probability, the pi, okay? Here, for instance, we have the pi is 0.20 or 20%, okay? So we're going to move all the way to 0.20, okay? So you have here the probability of success, which is constant. Here in this problem is 0.20. So now let's use the tables. It's much easier to use the tables when you have community probabilities, of course. So the first one, probability of x over 10 homes, which means probability of x equal 10, because we have 10 homes. So it's equal here 0.0. You can use the binomial formula, okay, plug 10 in the binomial formula, you come up with 0, or use this one here. We move to x equal 10 over here, then we move, of course, the table, all numbers inside the table represent probabilities, okay? Those numbers are probabilities. So now we move to 10 here, and the point of intersection between 10 and 0.20 will come up with 0.00. So this is the probability of x equal 10. Now the second part, less than 6 homes have solar energy, which means probability of x less than 6. Okay, we could use, as I said in the explanation of the lesson, that we could use the complement rule. So probability of x less than 6 is equal to 1 minus probability of x greater than or equal to 6, which is equal to 1 minus all those. Okay, 1 minus probability of x equals 6, x equals 7, x equals 8, x equals 9, and x equals 10. So these probabilities, we get them from here. You could use the binomial form, but it's so lengthy, and it's not straightforward at all. It will take a very long time. So instead of that, use the table. It's much easier and much fast. It gives you right away answer. So here 1 minus what if x equals 6? This is x equals 6. You come up with 0.06. As you can see, 0.06. What if x equals 5? X equals 6. Here we get a mistake. We're going to have a mistake. Plus is equal 1 minus what if x equals 6, plus x equals 7, plus x equals 8, plus x equals 9, plus x equals 10. And we're going to come with, of course, different number here. Of course, the probability of x equals 6 is going to equal 0.001. So let's add those, 0.01 plus all these zeros. So you're going to have over here 1 minus 0.001. Okay? So it's going to equal, of course, when we subtract this, you're going to come up with, of course, 1 minus 0.001, we come up with 0.99. So this is the probability, of course, of getting x less than 6. Of course, part C says at least 2 homes have solar energy. At least 2 homes, we're talking about probability of x greater than or 2, greater than or equal to. Here, of course, it's very lengthy to say probability of x equal 2 plus probability of x equals 6, 3 plus probability of x equal 4, 5, 6, 7, 8, 9, 10. So we use here the complement rule to simplify, of course, the calculation. So probability of x greater than or equal to 2 is equal to 1 minus probability of x less than 2. Okay? You have equal sign here. We get here without the equal sign in the right side. So 1 minus probability of x less than 2, which is equal to 1 minus probability of x equal 1 plus probability of x equals 0. Probability of x equal 1, that's 1 here, you get 0.268, plus probability of x equal 0.107, and 1 minus the sum of those, you get 0.625. So probability of x greater than or equal to is going to equal, 0.625. Now we move to part D, which says at most 3 homes have solar energy, at most, which implies maximum 3 homes. So it's going to be equal probability of x less than equal 3. At most 3 and down. So it's going to equal probability of x equal 3 plus probability of x equal 2 plus probability of x equal 1 plus probability of x equal 0. So here we come up x equal 3, 0.201, x equal 2 plus 0.302, x equal 1 plus 0.268, and probability of x equal 0 is 0.107. We put all of these and we come up with 0.878. This is the probability of at most 3 homes have solar energy. Now, what about the last part? None of the homes have solar energy. None of them, which means probability of x equals 0. Probability of x equals 0, come in here, 0.107. You can use, of course, the binomial formula, and you must come up with the same answer. Okay, now, problem number 2, or example number 2, it says hospital records show that 60% of patients suffering from chronic disease survive. 60% survive. In a sample of 9 patients selected at random, do the following. Find the mean and standard deviation of the distribution. Of course, here we have a binomial distribution. Let me answer the second question first, and then I'll move to the first question. Does the situation fit the requirements of a binomial distribution? We say yes. Why? Because an outcome of each trial is classified into one of 2 categories, either success or failure. The success here is survive. 60% survive and 40% die. So this is one of the requirements. Second requirement is that the random variable here counts the number of successes in a fixed number of trials. How many trials? We have 9 patients. Okay, this is the second one. Okay, that is satisfied. The third one is that they are mutually exclusive, the outcomes, because they are mutually exclusive. You can't have a patient at the same time survive and die, either survive or die. So they are mutually exclusive outcomes. Also, the outcomes are independent. Okay, the outcome of one trial does not affect the outcome of another trial. So they are independent. Okay, therefore, and we have a fixed number of trials, and then the probability of success is fixed in all trials, which is 0.60. Okay, therefore, yes, indeed, we have a binomial distribution because it, satisfies all the requirements of a binomial distribution. Now we move to that first question. Once it is a binomial, then, we can use the formula of the mean and the variance or standard deviation to calculate, its mean and its variance or standard deviation. So A, find the mean and standard deviation of the distribution. Because it is a binomial, then the mean of the distribution is n times pi. Mu equal n times pi. N is 9, and pi is given 0.60, therefore the mean is 5.4. The standard deviation is a positive square root of the variance, which is the square root of n pi, 1 minus pi. And then when you plug the numbers, the values of these, you come up with 1.469. Okay, now we move to part C. Part C says, find the probability that none of the patients survive. Here we're talking about probability of x equals 0. So probability of x equals 0, You can use the binomial formula, or you can use the table over here. Okay, each table will look like this. So now we're talking about x, the the random variable x, which count the number of successes. Okay, and then we have the probability. Okay, n equal 9 because we have 9, and then you have here the probability of success 0.60. So you have all these numbers equivalent to those, random variable of successes. Now here here it says find the probability that none of the patients survive, probability of x equals 0. What you get here is 0. Probability of x equals 0, we go all the way from 0 all the way to 0.60, and this is what we have, and the value is 0.0. You can use also the binomial formula, and you will come up with the same, result. Now, part D says find the probability that exactly 3 patients survive. So we're talking about x equal to 3. The random variable x is equal to 3. So probability of x equal to 3, you can use, as I said here, the random you can use the binomial formula to calculate the probability, or you can use the table. So probability of x equal 3, 1, 2, 3 here, move to here, okay, we come up with 0.074. 0.074, okay, 0.074. Now, part E says find the probability that more than 5 patients survive. So we say probability more than it's a keyword, which means greater than. Okay, so probability of x greater than 5. Probability of x greater than 5. Okay, which is equal probability of x equals 6 plus probability of x equals 7 plus probability of x equals 8 plus probability of x equals 9. So when we add all these probabilities from x equal 6, 7, 8, 9, 6, 7, 8, 9, you add all these, you come up with, 0.482. Okay? Now, find the probability that at least 1 patient survive. At least mean, 1 and more. Probability of 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a lengthy, calculation. So it's easier to use the complement. So probability of x, so find the probability that at least 1 patient, probability of x greater than or equal 1 is equal to 1 minus probability of x less than 1. This is much easier to calculate, when you use the complement than using the probability of x greater than or equal to 1, which is equal to 1 minus probability of x equals 0. Okay? So which is equal to 1 minus 0, which is equal to 1. So the probability of at least, 1 patient survive is equal to 1. G, find the probability that more than 7 patients survive. More than 7 patients survive. So it's going to equal probability of x greater than 7, which is equal probability of x equal 8 plus probability of x equal 9. Okay, it's here. It's not, of course, it's not easier to use the complement here because you only add only 2 values, probability of x equal 8 plus probability of x equal 9, and then when you look over here, x equal 8 and 9, 0.060 plus 0.010, and you come up with, of course, 0.231. Okay? You got 0.070. Okay? Now we move to H. Of course, H says find the probability, of course, at least 7 patients survive. At least, mean probability of x greater than or equal to 7. So I got here probability of x equals 7 plus x equals 8 plus x equals 9. And then when you look at the table, you can find all these probabilities from the table, okay, and you come up with 0.231. The last one, find the probability that less than 7 patients survive. Less than 7 patients, to probability of X less than 7, as you can see here. So here, of course, you use the complement rule, which is easier to calculate and add those probabilities. Okay, and then when you use the complement rule, then you will get 1 minus probability of X greater than or equal to 7. We use greater than because probability of X less than 7, we start from what? Probability of X equal 6 plus probability of X equals 5 plus probability of 4, 3, 2, 1, and 0. Here we want the complement, so we say what? Probability of X, 1 minus probability of X greater than or equal to 7. Okay? Because, less than 7, probability of X less than 7, it means what? All probabilities from 0 to 6. So we want what? We want the complement of this, which are 7, probability of X equals 7, plus probability of X equals 8, plus probability of X equals 9. Okay? And we come up with these things here. When you do the calculations, okay, you come up with 0.769, and this is the result of the probability of X less than 7. Okay, now we move to solving another example, which is problem number 3. It says, historically, 10% of the applicants at the university failed in the entrance exam. Failed. Here, the probability of success. Here, success is failure, actually. So, as we said when we discussed the concept in the chapter, we said, success or failure do not mean good or bad. Okay. Success doesn't mean it is good and the other is bad. Okay. So in a group of 15 applicants, here we're talking about the number of trials is 15. The number of trials is 15. So n is equal to 15. Determine the values of n and y. Of course, n is 15. N is 15 here. N is 15. And y is 0.1. Now this B says, does the situation fit the requirements of the binomial distribution? Already we discussed that in previous example. We said, yes, indeed, it does fit the requirements of a binomial distribution because, an outcome on a trial is classified into one categories, either a success or a failure. The success here is failure, is fail. We have 10% of the applicants failing, and 90%, passed. So you have failure and, not failure or passes. And also, the random variable, of course, the random variable X counts the number of successes in a fixed number of trials. The fixed number of trials is n, 15, okay? And the random variable will count the number of successes here. It will count the number of failures, okay? And as you see here, the third, as you can see, the trials are independent, okay? The trials are independent, as you can see. And also, the outcomes are mutually exclusive. You can't have, an applicant fail and pass at the same time. Therefore, the outcomes are, mutually exclusive, okay? So, therefore, the situation here fits the requirements of a binomial distribution. Now, comment on the shape of the distribution. Of course, it is positively skewed since by, the probability of failure is 0.1, which is less than 0.5. Okay, therefore, it is positively skewed. And when it becomes 0.5, it becomes, normally distributed. Define the standard deviation of this binomial distribution. Of course, the standard deviation, as you said, it is the positive square root of the variance, and the variance is n pi into or times 1 minus pi. So when we get the square root of 15 times 0.1 times 0.90, we come up with 1.16, which is the standard deviation of the distribution. How many students do you expect to fail? Here we're talking about the mean of the distribution. Of course, the mean is n times pi. Mu equal n times pi, n is 15, pi is 0.1, it's 10%, which is fixed. The probability of success is fixed, and the probability of failure is fixed. Probability of success here is 10% of applicants fail, and the probability of failure is 90% of students who pass. So this is how we can translate them, okay? Now use either the binomial formula or the binomial table to answer the following. Of course, using the binomial table is much easier to do these problems because, as you see, the table is here. So all you have to do is just, look at the table and find the probabilities of any, binomial value. Okay, look over here. What is the probability that exactly one fails the exam? Probability of x equal 1. That's 1 here, okay? This is 1. This is x, 1. Probability of course, success or failure here. Probability of x equal 1 is 0.343. 0.343. Okay? From the table, you just see, pick it up, directly from the table. Okay. You can also use the binomial formula to calculate the, this probability. G, what is the probability that at least two fail the exam? Of course, probability of x greater than or equal to 2. Of course, here we have 15, so it's better and easier to use the complement here in order to calculate the probability of at least two failures. Two fails the exam. So probability of x greater than or equal to 2, of course, if you don't use the complement, then you're going to calculate probability of x equal 2 plus probability of x equal 3 plus probability of x equal 4 plus probability of x equal 5, all the way to the probability of x equal 15. So it is so lengthy. So it is better and easier, to calculate or to use the complement of this to calculate the probability of x greater than or equal to 2, which is equal 1 minus probability of x less than 2, which is equal probability 1 minus probability of x equal 1 plus probability of x equal 0, and these are given here. Probability of 0, 0.206, probability of 1, 0.343. We plug them here, of course, and they come up with 0.450. Okay, 0.450. What is the probability that exactly one passes the exam? Look, here you know that the probability of failure, 10%, is 10%. Now let's talk about what passes. So let us transform the probability of failure, which is success here, which is 10%, to a probability of passes, which is 90%. As we said, one of the requirements of the binomial distribution is that the probability of failure is fixed and the probability of success is also fixed. Here we have the probability of success is 10%, but actually it's failure here. So what is the probability of passes? It's going to be 90%. So here we say, if probability of pi, which is probability of success here, is 10%, then probability of 1 minus pi is, which is probability of passes, is 0.90. So we use this one, probability of 1 passes. Now we have to move to 0.90 because this is the probability of passes now. So probability of 1 passes, this is 1 passes, is 0, so it is 0. Okay? Now, also, to complete the question, we have also two other parts. Let's erase over here. Okay, and the question says, of course, also we have another part of the question that says, what happens, say, on part 2 here of the question, it says, what happens to the skewness of the distribution if A for the same probability of success which is 1 here, which is equal to 0.1, so over here, and becomes larger. Of course, here the answer, if you remember, when we discuss these important issues, we said that, of course, as n becomes larger, okay, the answer here, the distribution becomes more symmetrical. Okay, becomes more symmetrical. Okay, now B it says for the same n for the same n, the number of tries, which is 15, the probability of success becomes greater than 0.5. The same thing, we discussed that, okay, in this lesson, and we said when n remains fixed, okay, and the probability of success becomes greater than 0.5, then the answer, of course, answer here, the distribution becomes negatively skewed. Okay, so these were explained, in the lecture. You just go back and see what we did in the explanation of the concepts in this chapter.